not looking at 7.2, but we're going to stick with our wavelength of light that has, what was it, 670 nanometers of light. If that's the wavelength, we might be asking ourselves, what is the amount of energy associated with that amount of wavelength of light? And so we can find our equation, energy equals Planck's constant times frequency, but we remember that frequency is equal to the speed of light divided by the wavelength. So I'm just going to put that in here, speed of light divided by the wavelength. There we go, speed of light divided by wavelength times Planck's constant. So the energy for this particular reddish light is going to be 6.626 times 10 to the negative 4 joules times seconds. And we're going to multiply that by, let's see, we calculated that back in that previous slide. I'm just going to use that same value. If I can find it here, 4.78 times 10 to the 14 hertz. 4.78 times 10 to the 14, and that was 1 over seconds. Now it's important to notice here that the seconds, one is upstairs and one is downstairs, so we do come out with just a unit of energy. We come out with joules. And that calculates out to be 2.97 if we round it. 2.97 times 10 to the negative 19 joules. So one photon of light does not pack a huge amount of energy, but remember, you're talking about many moles of these if you're looking at any significant amount of light like fireworks and things like that. So another thing we're often interested in, in fact the reason we're bothering to look at this for our chemistry class, is we're looking at electrons that have become excited. And so if we look at electrons maybe down here in the ground state, if we're just talking about the hydrogen atom here, you know that the ground state, the one electron in hydrogen, its ground state would be at the lowest energy level, the energy level 1. Well, if we put in some energy, we can excite that electron. And we might excite it up to, let's see, I'm just trying to match the second energy level, or we might even excite it up to the third energy level. And this distance here, by the way, is not to scale. There's not room for me to do this to scale on this particular slide. But we can excite the electrons either with electricity or mechanically or with a flame, or however we might excite these electrons. So they're going to jump up to some higher energy level. Now when these electrons fall, as you know, if you have a big sample of hydrogen, there's going to be some of them falling, and as they fall, if they fall this distance, they're going to release a different wavelength of energy than if they fall this distance, clear down to the first energy level. Well, it turns out that if they fall this distance right here, the wavelength is going to be long enough, the wavelength is going to be short enough and the energy is going to be high enough that we cannot see this light. This is going to be down in the ultraviolet end of the spectrum. So here you see transitions from various wavelengths, various energy levels down to the second energy level, and these can produce visible light. And so for ages, at the turn of the century, the beginning of the 1900s and late 1800s, early 1900s, people looked at this and we're puzzled. What causes this? So that was one of the big conundrums. And this model, the Bohr model of the hydrogen atom that was around at the time, eventually it was proposed that this explained why we see different wavelengths of light when we look at the hydrogen spectrum through a prism or through a diffraction grating, as we have been looking at in class. So this is a wavelength of some kind of light that came into our spectrometer that we've been looking at in class. And we might ask the question, if we're looking at this peak right here, and I'm going to call this the middle of the peak. So if this is 500, 600, 700, so this is maybe 640. At a wavelength of 640 nanometers, you should be able to calculate the frequency and energy associated with that wavelength. So that's the kind of problem you need to work on and be able to solve. So practice that a bit, see what you come up with. And in case you've worked those problems, that should be the answer.